We are going to review uniform circular motion today. So uniform circular motion, it means a motion of object traveling at a constant speed on a circular path. So just as in the picture, this is the center, and the airplane is going along a perfect circle path with constant speed. Now pay attention, is constant speed is not constant velocity, because see, the velocity of the airplane is always tangent to the circle whenever the airplane is, which means the direction of the velocity is changing over time, constantly changing over time. So it's not constant velocity, it is constant speed for uniform circular motion. And the word uniform captures the feature constant speed. So apparently, let's call the time it takes for the object to travel once around the circle. So the distance it traveled will be the circumference of the circle. Circumference of the circle would be 2 pi r, and that's the circumference. Now the time it takes to travel one circle, we call it the period t. So apparently the velocity of the object should be 2 pi r over t. So that's the velocity of the object. And then we derived during our class that there is an acceleration associated with this motion. We call it a centripetal acceleration, is AC, and it should calculate as v squared over r. Now, whenever the airplane is at a place, the velocity of the airplane or any object doing uniform circular motion is tangent to the circle, and the centripetal acceleration is pointing to the center of this motion. Now, from Newton's second law, if you have an acceleration, then there got to be a net force acting on the object, which should be, and the force should always equal to ma. So if you have a centripetal acceleration AC, the centripetal force Fc should be mac, which turns out to be mv squared over r. The centripetal force should be mv squared over r. So let's do our first example. Let's try to first calculate the velocity of the Earth orbiting around the Sun. So we discussed the time it takes roughly 8.5 minutes for the light to travel from the Sun and the Earth. So you can calculate the distance between the Earth and the Sun. And we have measured that the distance between the Earth and the Sun is roughly 1.5 10 to the 11th meter. We know, everybody knows, that the Earth orbiting around the Sun for one complete circle in 1 year. So first of all, we need to convert 1 year to SI unit, which is second. We convert 1 year to second. It will be 1 year. We roughly have 3.1 up to 10 to the 7th second. So what would be the orbiting velocity of the Earth around the Sun? So from what we discussed before, velocity of the Earth should be 2 pi r over t. So we plug in all the numbers r and t. We find orbiting velocity of the Earth is roughly 30 kilometers per second. So after we find that the velocity, we can calculate the acceleration, centripetal acceleration of the Earth, right? AC of the Earth should point into the center of the motion, which is the Sun. AC of the Earth is v squared over r, which turns out to be a very small number. Now, after you find the AC, we can calculate what's the centripetal force that keeps the Earth in its orbit. So we need to know the mass of the Earth. Now, the mass of the Earth, if you Google it, it would be roughly 5.9 10 to the 24 kilograms. So you plug in this number, you find the force is roughly 3.6. Okay, we'll come back to that when we do a review of gravity. So this is basic calculation of uniform circular motion, calculating velocity, centripetal acceleration. Okay. Now, you have noticed if we want to make a turn on the highway, when we make a turn, the road is not level, it's actually banked, it has an angle. And this is help us to make a turn. So suppose we don't want any friction of the car in this horizontal direction, in the x direction. So the car can have friction in the direction it's moving forward, but we don't want the friction this in the x direction as in the plot. Let's call this y direction. So if you have a banked curve, it looks like the car is doing uniform circular motion along this circle. And then you will have a radius of this circle. Let's call it r. And we want to know what will be the velocity. If you know the r, if you know this angle theta, what will be the optimal velocity that you don't have any friction in the x direction. So what we need to do, in this one, we need to do free body diagram as all the dynamic problems. So for the car, we have Fn acting on it, and we have mg acting on it. Now, using some geometry, you can find that this angle equals theta as well. So we can build dynamic equations in the x direction and in the y direction. So it's kind of easier in the y direction because the car has no motion in y direction, so the acceleration in the y direction is 0. So net force in the y direction is 0. So you can have Fn cosine theta equals mg. That means the net force in the y direction is 0. Now in the x direction, does the car have any direction? And the answer is yes, right? Because the car is doing uniform circular motion, so it will have AC pointing in the negative x direction. And AC should be, if we know the velocity, AC should equals to v squared over r. That's what we have learned for uniform circular motion. So the net force acting on the car is mv squared over r in the x direction. Now, where is that force coming from? There are only two forces acting on the car, normal force and mg. So, which means, and mg doesn't have an x component, only Fn has x component, so you should have Fn. The x component of Fn should be Fn sine theta. Give you the net force on the car in the x direction, and it should equals to mv squared over r because the car is doing uniform circular motion. So we just solve for v from equation 1 and 2. So what we can do is we have equation 1 divided by equation 2, which means you have left hand side of equation 1 divided left hand side of equation 2. Right hand side of equation 1 divide right hand side of equation 2. So you have tangent theta equal v squared over gr, which turns out give us v over gr tangent theta. Now let's look at one more example. So we have a conic pendulum, and the ball is hanging on a string. The string is doing uniform circular motion around this circle with radius r. Now r equals to L. See, r equals L sine theta. So we want to find out what will be the speed of the ball if we know L, we know theta. So we still need to do free body diagram. There are only two forces acting on the ball. We have tension Ft, we have gravity mg. So let's build our coordinate system x, y. Again, in the y direction there is no motion, so we have net force equals 0. Ft, this is theta. Cosine theta equals mg, just in the y direction. In the x direction, the ball is doing uniform circular motion, so it have AC in this direction, and it equals to AC equals to v squared over r. So its net force is mv squared over r in the x direction. And the net force is coming from the x component of tension, Ft sine theta. So we can solve for velocity of the ball. So first of all, from equation 2, say we can have Ft equals g over cosine theta. And then we place Ft into 1, we get mg cosine theta. This is Ft times sine theta equals mv squared over r. You can just solve for it, and in the end you should have velocity equals gl tangent theta sine theta. And you find that if your velocity is larger, you will have a larger angle theta from this equation.